Welcome everyone. Let's have a look at problem 16.1. We're asked to find the largest approximation error when the weighting filters are used to express constraints on the sensitivity, the complementary sensitivity, and the control sensitivity for a seesaw system. And the controller is designed to satisfy this. So let's again quickly recap what we want when we define shaping filters. So let's take the example of sensitivity. Yes, a typical shape of the sensitivity is something like this. You bring it down, and what we want is to impose a filter. We want is to impose that the sensitivity lies below this filter. So this is 1 over ws of s. Now because this is a seesaw system, it's just absolute value of s. So what we want really is that s of j omega should be less than 1 over less than or equal to 1 over ws. Let's call this ws of j omega for all omega, and this is then nothing but ws of j omega times s of j omega less than 1 for all omega, and that is nothing but the h infinity norm, or the maximum over all omega. So recall that this is nothing but the supremum over all omega of so if the supremum over all omega is less than 1, then this is true, and this is true only if the maximum over all omega is less than 1. So that's clear. So this is what we want if we want to shape the sensitivity. Now if we want to shape S T and Ks by shaping filters Ws, Wt and Wk, then what we really want is that so what we really want is these three conditions to hold. So let me say this holds, and this holds, and this holds. Now for simplicity, or for making the notation simple, let's call this G1, let's call this G2, let's call this G3, so we don't have to write all these WSS, WKKS all the time. So we want the H infinity norms of these three to be separately less than 1. Let's call this 1. This is what we want, and what we are instead imposing is that the H infinity norm of G1, G2, G3 together is less than 1. So now this is a MIMO system. We had a seesaw system, and we wanted 3 conditions to hold, and now we define a new MIMO system, which is a single input 3 output system. We want the H infinity norm of this to be less than 1. So that is nothing but supremum or omega maximum singular value of G1 of J omega, G2 of J omega, G3 of J omega to be less than 1. And now this is a 3 by 1 vector, so we know that the singular value is for a vector is just the 2 norm of that vector, so that is nothing but and now if this holds for, if we want this to hold for the supremum or all omega, that is nothing but saying that we want this to hold for all omega, and that is nothing but saying that squaring both sides. Now note that this clearly implies 1, which is what we want. So what we are imposing is clearly making sure we get what we want, but probably it's imposing more than what we want, and this is really the exercise. We want to find how much more conservative is our imposed condition than what we want. So before we see this gap for our example, let's look at it for a 2D example and give it a geometric interpretation. So what we want is that G1 of J omega and G2 of J omega should be less than or equal to 1 for all omega. Now if we want to show this graphically, what we want is that if we plot G of J omega absolute value on the x-axis and G1 of J omega on the x-axis and g2 of j omega on the y-axis, we want all the points to lie within this box. But what we instead impose is that g1 of j omega squared plus g2 of j omega squared is less than or equal to 1, which is, if you notice carefully, the equation of a circle. So what we impose is that the points should lie within this region. So the remaining region is the amount of conservatism that we add. So clearly, if you are inside the circle, you're also inside the box. So if we impose this condition, we clearly get what we want, but we impose a stricter condition in that some points which could have been okay are now not okay because of the stricter condition. And now we can then find uh, the error in this sense. So this distance could be found out to be 1 minus or rather, so this is 1 and the whole thing is root 2, so the root 2 minus 1. We can also define the error as the ratio of this line over this line. In that case, it would be 1 over root 2. So that would be this distance divided by the whole distance. Now we can go to our 3D case where we have, so where we want less than 1, and if we again plot this in the form of a sketch, so let me also write what we impose instead. So we can now bring a sketch. So now we have this as the equation of a sphere. If we plot g1, g2 and g3 along the x, y and the z axis, and now the imposed condition requires the points to lie within the sphere, and what we wanted was to allow all the points in this box. So the conservatism is the remaining volume, and if we want to find the error in terms of this length divided by the maximum length, we can see that that would be 1 over root 3, because this length is root 3 and this is 1. So that's it for this problem, and thanks a lot.